I want to talk about partial fractions, but before we get there, we really have to start with what do we do when we look at a rational function? Why is it rational? Because I have a polynomial divided by a polynomial. When we know that we have a rational function, there's kind of a flow chart of what we're going to decide to do. So the first thing that I want to check always is for a u substitution. Typically for a rational function, that's going to mean, is the derivative of the bottom equal to the top? Well, in this case, the derivative of our denominator is 2x minus 6, which is not what we have on top. If we don't have a u substitution, then I'm going to check the largest powers of x. So I'm checking those powers to see where is the biggest power. If that largest power is in the numerator, or if the powers are the same, that's going to lead me to doing long division as a first step. If my biggest power is in the denominator, then I'm going to check, does the bottom factor? If it does, then we're probably going to need to use partial fractions. If the bottom doesn't factor, then really the only technique we have is to hope that secretly it was an inverse tangent problem. Most of the time, if we've gotten this far in 17b, the denominator is going to factor and we should be thinking about partial fractions. If we follow this flow chart for this problem, we already checked for the u substitution, wasn't there. So now I'm looking for where's the biggest power. Well, my denominator has a power of x squared, and the numerator is linear. It only has a power of x to the 1. So we find ourselves down here. Biggest power is in the denominator. Now I'm going to see, does the bottom factor? Looking at that denominator, I can factor that as x minus 7 times x plus 1. So yes, the bottom does factor, and we should be thinking about partial fractions. I'm going to erase this flowchart so that we can get into the problem. Thinking back to algebra, what's happening with partial fractions is a little bit like we're saying, if I had 3 over 7 and I was adding that to 2/5, we know that we'd need to get a common denominator, and that common denominator would be 35. What partial fractions is doing is saying, well, what if I know that over here my common denominator is 12? What were my possible fractions back here? So my possible denominators were 2, or 3, or 4, or 6, or 12. All of the factors of 12. When we think about that for a polynomial, that means in this case, we're breaking up this fraction that we have. We're trying to break up the 2x plus 1 over x minus 7 times x plus 1. And we're saying that must have come from something that looked like it had denominators of x minus 7 and x plus 1. The thing is, we don't know what goes on top. So we put placeholder variables in there. I'm going to put an A and a B. There are two methods to work through these partial fraction problems, but they both start off in the same place, which is if this equation is going to hold true for all values of x, then I ought to be able to multiply both sides by that common denominator to eliminate all of the fractions. And if you're thinking to yourself right now, wait, it's not going to be true if x is -1 or x is 7, we're going to take care of that in the next section of the textbook, in section 5.8. Over here on the left-hand side, everything's going to cancel, and I'll be left with 2x plus 1. And over here on the right-hand side, if I distribute this in, when this gets distributed into the first part, I'm left with a times x plus 1. And when it gets distributed into the second part, I end up with b times x minus 7. This is where our two methods of solving for partial fractions really start to diverge. So I'm going to show you the method that comes first in our textbook, and then I'll show you the version that I like better. The truth is, both methods work in every case. Usually for each problem, one method ends up being a little bit faster than the other. So the method in our textbook would have us multiply out both sides of this equation and then do something that gets referred to as matching coefficients. If I distribute the a and I distribute the b, I would end up with ax plus a plus bx minus 7b. When we say matching coefficients, we mean on the left-hand side, we know the coefficient of x is 2. So on the right-hand side, the coefficient of all of the x terms must also equal 2. Pairing these up, I'd have 2x is equal to a plus bx, or sorry, didn't need an x. Or 2 is equal to a plus b. Coming back and looking again at the left-hand side, I have a 1 without an x, which means all of my terms on the right-hand side without an x must add up to equal 1. Whenever we use this method, we end up with a system of equations, and we can use any of our algebra skills to solve that system of equations. I happen to like substitution, so I think that's what I'm going to choose here. Thinking about these two equations, this one could be rearranged to say a is equal to 1 plus 7b, and that can be substituted in this other equation. Which should leave me with subtracting 1 from both sides. I'd have 1 is equal to 8b, where b is equal to 1/8. Once, think about the substitution method, once I've solved for one of the variables, I can plug it into either of the original equations to get the second variable back. I'm going to choose to plug it into something that already says a equals, so I'm basically done. Since a equals 1 plus 7b, that means a equals 1 plus 7/8, or getting a common denominator, 1 is 8/8, so that's 15/8. All of that work was the algebra part. We still have to do the calculus. And the calculus part says, that a value of 15/8 belongs in the numerator of a fraction above the x minus 7 term. And that value of 1/8 for b belongs in this fraction above the x plus 1 term. We're swapping out the original integral for two that are easier to work with. And both of those, we hope we can quickly recognize as being natural log. So I've got 15/8 ln of x minus 7. Sorry, ln of absolute value of x minus 7. Plus 1/8 ln absolute value of x plus 1 plus a constant. I said that there were two methods for finding the constants doing this partial fractions, and now I'm going to show you the other method. We start off with the same steps to do the other method, but instead of expanding this out, we're just going to choose nice values of x to plug in. And the nice values of x I'm going to choose usually are anything that make a part of this equation 0. In this case, I'm going to choose x equals -1 and x equals positive 7. So if I plug in x equals -1, I'm going to plug that in everywhere in the equation and get 2 times -1 plus 1 is equal to a times -1 plus 1 plus b times -1 minus 7. 2 times -1, I'm at -1. Sorry, I'm at -2 plus 1 overall would be -1. The whole reason we chose -1 is so part of this would go to 0. And here I've got -8b. Which gives me the same value that we had before, that b must be equal to 1/8. Our other nice number that we're going to choose is x equals 7. Plugging x equals 7 into our entire equation, I have 2 times 7 plus 1 is equal to a times 7 plus 1 plus b times 7 minus 7. Again, we chose 7 to make part of this go to 0. 2 times 7, I'm at 14 plus 1, that's 15, is equal to a times 8, which gives us the same value we had before, that a is equal to 15/8. And then from there, we would finish it off the same way that we finished off the first one.